Howdy ho. So this is the final lecture we have on chapter 6, where we are looking into the semiconductor physics, the 101 in there, and the associated solid state physics. So here in this very lecture, we will introduce to you a Hall effect. And Hall effect is a quite important effect in terms of semiconductors, and also in terms of the kind of history of physics, in terms of like understanding what are metals and what gives rise to electrical conductivity. But mainly the Hall effect is important because it enables people to measure the concentrations of carriers, and in addition it also allows people to measure or quantify the type of the majority carrier. So is it a negatively charged quantity or positively charged quantity? And related to this Hall effect and subsequent measurements of Hall coefficients of metals, mainly elemental metals, convinced at the time physicists that electrical currents in solids are really mainly due to freely moving electrons and not by freely moving positively charged objects such as protons or something similar. So although aluminum was a puzzling exception, the behavior of elemental metals, most of the metals were found to have a negative Hall coefficient, meaning that it's really electrons that are giving rise to the electrical conductivity. So Hall effect also has this kind of historical importance related to it. But let's now get started with the actual thing. Like we have quite a bit of things to discuss and discover. So I will start by taking a quote from Edwin Hall's paper, and recall this is a Hall effect we're describing. So Edwin Hall was the kind of main inventor of the effect. So Rowland was Edwin's PhD supervisor, and this is a direct quote. So Rowland now advised me in repeating this experiment to use a gold leaf mounted on a plate of glass as my metal strip. So it warms my heart as a PhD supervisor to see that back in the days, at least, the PhD supervisors also knew how to do experiments, as that seems to be the kind of contrary now, at least. And at least 100 years ago, professors still knew how to do things in the lab. At the time when they have managed to become professors, and they have happily forgotten all the details of how they got that far, so how to actually do experiments in a lab. But okay, let's get back to this. So Edwin did so. So he was listening dutifully for his PhD supervisor, and good for us that he did. And experimenting as indicated above, he succeeded in 28th of October in obtaining the effect of magnet's action, a decided deflection of the galvanometer needle. And this is, of course, before internet and before iPads and even before computers. So I guess doing experiments was quite a bit different at that time. So a little bit different kind of experimenting was going on in labs 100 years ago. In short, the phenomena observed were just as we should expect to see if electric current were pressed, not moved toward one side of the conductor. And this is by Edwin Hall, and from 1879 seminal paper where he was first time discussing Hall effect. And please note here, like what he wrote, like the electric current were being pressed. So it seemed that there's a force that is pressing electrical current sideways in a material and doesn't really move them as such. Because like when you open up the Wikipedia article of a Hall effect and other locations in the internet, sometimes it may look like the case that the electrons also are being moved due to a Hall effect, but I would rather just say that there's a force that seems to be affecting their motion. And this force manifests itself as a change in the kind of potential sideways in the piece of our solid we are measuring, but more on that later. So this excerpt that we see here is from the Hall's original paper regarding the Hall effect. And this is a phenomenon that happens in a conductor, in a semiconductor, in a piece of a metal that is being placed under an external magnetic field. So under an external B field. And why this effect is quite important in solid state physics is that it really helps us, or in fact it allows us to measure carrier types and their concentrations. And the most important thing here is that it allows to quantify the carrier types. So is it a positively charged quantity, such as a hole, that is giving rise to the electrical conductivity, or is it a negatively charged particle like an electron? So this is why Hall effect has its historical importance. And of course, it allows us to measure the carrier concentrations. So also this is very important in terms of the modern day semiconductor physics and making of semiconductor devices. So let's now go through the effect and what happens in the effect. And let's start by considering a conducting solid. So it could be a metal or it could be a semiconductor. And we have a macroscopic electrical current flowing through the solid. So we have an electric current J that flows through the piece of a material, highlighted in this picture. So we have the current here flowing, let's say, in the positive x direction. So in essence, we have electrons, in fact, moving in the negative x direction. And this is the scenario we are considering. And here we have the external magnetic field that will be then deflecting, affecting the motion of electrons. So when this external magnetic field is being applied, of course, the flow of charges will be changed. And the flow of charges, please remember how it's being defined. So J, the flow of charges, is essentially, this is the current. It's the charge Q times the velocity of electrons. And this quantity, this flow of charges feels a Lorentz force. So please recall the Lorentz force F equals QE, where Q is the charge of our charged particle, E is the static electric field, or just an electric field. Of course, Lorentz force applies also to electrodynamics. So, and then we have the contribution to the magnetic field. So we have the Q times E times B. And this cross product with the velocity of the electron times the magnetic field is the one that we are considering here. So for simplicity, let's consider a case that we don't have any external electric field. We only have an external magnetic field, and subsequently the force that these charged particles, the electrons that are moving, or they could be, of course, holes that are moving through our piece of a solid. What happens is that then we have the cross product of J with the magnetic field. So a force is being created, and knowing the properties of a cross product, we see that this force that is being created actually points in an opposite direction with respect to the J and P. And now, already spoiling the fun, let's look in which directions the J is pointing. It's pointing in the X direction, and the magnetic field in here, it happens to point out along the Z direction. So we know that this force must be pointing somewhere along Y direction from the properties of the cross product. So for simplicity, let's just consider a case where the magnetic field is only pointing along the Z direction. So then it has the amplitude be Z, and it's only pointing along the Z direction. So the Z hat is our unit vector pointing along Z. And we only consider the case that the current is only flowing along the X direction. So this is also the kind of for conceptual clarity of things. And now, as mentioned, the Lorentz force gives rise to a force, and this induced force now points along the y-axis. So in other way of saying, F, the vector, is of a form that we have the amplitude of the vector Fy, and it's pointing along the y direction. So y hat is our unit vector pointing along y direction. And this is a force. So it presses the charges, and in fact, it doesn't really move them as such. Of course, when the time progresses, it may start moving them around, but what it does in the first place is that it gives a force. It presses the charges. And this kind of force, of course, we can interpret that as an electric field. So please recall the Lorentz force again. So F equals Q times E. And now this E here is the kind of field that is known as the Hall field. So instead of measuring a deflection of currents, we are actually measuring a voltage difference between these two side walls of our device. So through the Lorentz force, we see that this external magnetic field, it pushes the electrons, and this deflection can be seen to be giving rise a potential difference, and that can be measured. And when we measure it, in essence, it will be the Hall field. And now we can estimate what is this effect in strength. So we can just require that these two forces, they can be equal, and this in fact they are. And in fact, then we get a relation that the Q times EH, where EH is the Hall field, this must be equal to the Jx times the magnetic field's amplitude Bz. And we solve this for a total charge, or its inverse, and what we are left over is that we then have the Hall coefficient. So Hall coefficient is being defined that it's the inverse of the total charge Q, and when we place this from the previous equation, what we get is that the Hall coefficient RH is of the form EH divided by J times B, and this RH is our Hall coefficient. So simple as that. And now the interesting part is that when we have a negatively charged carrier, so when we have an electron, the RH is given by a factor like this. So we have 1 over Q. So in fact, what we have here, we will have a minus 1 over N times E. So this Hall coefficient for a case of negatively charged carriers is negative. And this is nice. And even more nice is the fact that if we would have a positively charged holes, the Hall coefficient, in fact, similarly defined, would be of a form that we have 1 over P, the carrier concentration of holes in the valence band, times E, and this is of course a positive quantity. So this is the main thing that we must remember when we are thinking of a Hall effect and the Hall coefficients. So if we have negatively charged electrons giving rise to the electrical conductivity, the electrical current, the Hall coefficient we would measure is negative, and if it would be the other way around, we would actually have a positive quantity to measure. And this is in fact, even though it does not seem to be much, it's not easy to measure what is the sign of your carriers, because the kind of like a macroscopic current is actually not being changed. Would you have positively charged quantities flowing in the opposite direction or electrons moving in the opposite directions? And you don't easily distinguish which are the carriers, what kind of types of carriers you have in your solid. But if you take use of the Hall effect and you measure the Hall coefficient of your material, then you can actually estimate, you can actually quantify what is the type of carriers that you have in your system, in your piece of a solid material. And like I already said twice, from the historical point of view, the Hall effect and the subsequent experimental values for RH, the Hall coefficient for metals, they were the first experimental verification that electrical current is actually being carried in most cases by electrons. And this was a big thing more than 100 years ago in the beginning of the 20th century, so 1900s. This was a thing that people did not really know. And of course, now it seems silly, but during that time it wasn't clear, and some people were considering that maybe it will be positively charged protons or something else that could give rise to electrical currents. And I guess it's related to this fact that somehow the way we have defined what an electrical current is, that the electrical current actually is being defined as the direction that is opposite to the actual movement of electrons. So I guess that's a good example telling us that this was not a trivial piece of information to understand back in the days. And finally, let's just generalize the treatment. So if we would have a more general case of a semiconductor and we would make a Hall coefficient measurement, we would measure what would be the Hall coefficient. These carrier types, the fact that we may have both electrons and holes residing in the semiconducting material, the Hall coefficient can be estimated via these kind of equations. So the Hall coefficient for the general case that we have both types of carriers present in the material, the Hall coefficient is of a form that we have in the denominator. We have the whole concentration P times the whole mobility squared minus the electron concentration at the conduction band N times the electron mobility squared. And we have in the denominator, we have the electric charge. In the parentheses, we have the similar terms. So we have the whole concentration times the whole mobility plus the electron concentration times the electron mobility squared. So here, mu E is the electron mobility and UH are the whole mobilities. So this is how we could estimate and measure the Hall coefficient. And of course, in principle, we would get information of what are the carrier concentrations of our piece of a semiconducting solid. So now I rest my case. We are done with the chapter 6 in our course, and I'm happy for you that you made it this far. And please join me in the final chapter where we are discussing mostly dielectric materials, so insulators. I thank you, and please enjoy the rest of the day or evening or night in your life. Thanks and bye-bye.